Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and we are here today at Fan Mountain Observatory. Fan Mountain is the dark sky site that's operated in central Virginia by the Astronomy Department. Back in the 1960s, the Astronomy Department was operating McCormick Observatory on the grounds of the University of Virginia, when it was realized that light pollution was going to be a problem for the research that was carried out there. So the search began for a new dark sky site. And after a few years, they settled on Mount Oliver, which is in the Fan Mountains, and that's the origin of our Fan Mountain Observatory. Now, Fan Mountain used to be an apple orchard decades ago, and the top of this mountain was cleared and filled with apple trees. Today, on the other hand, it's filled with telescopes. And these telescopes are still used for research and for education and for public outreach by the Astronomy Department. The first telescope was put here in 1967, and that was followed 5 years later by the giant 40-inch telescope just over my shoulder here. There are a couple smaller telescopes on top of the mountain as well, including a fully robotic telescope that's owned by Norfolk State University and operated by us here in the Astronomy Department at the University of Virginia. So let me take you on a tour of these telescopes. We'll go inside, we'll talk about what the telescopes used to be used for, what they're used for today, and a little bit about how telescopes work. So please join me as we look through the telescopes here at Fan Mountain Observatory. One of the first telescopes put at Fan Mountain Observatory is this 10-inch astrograph. It had been in use at McCormick Observatory for many, many years, when it was moved here to Fan Mountain Observatory in 1967. The astrograph was used at McCormick Observatory for doing surveys of the sky. And in particular, one of the astronomers, used this telescope to look for dim red stars, whose distances could be measured using the large telescope at McCormick. Now, since this telescope came up here in 1967, we really haven't had much use for it. So today this telescope is retired and it's no longer in active use. It's a 10-inch astrograph, which means it's got a lens up at the front that's 10 inches across. In fact, it's got 3 lenses up front that are 10 inches in diameter, and it was used primarily with photographic plates. This telescope has not been modified to use modern digital cameras, which is one of the reasons that we don't use it today. The first big telescope to be built here at Fan Mountain Observatory is the 31-inch telescope that was finished in 1967. At McCormick Observatory, on the grounds of the University of Virginia, we have a 26-inch refracting telescope. That is, it's a lens telescope, has 2 lenses that refract or bend light and bring it to a focus, and it's 26 inches in diameter. That telescope was used for measuring the distances to nearby stars and for measuring precisely the motions of stars through our night sky. In the 1960s, the Astronomy Department wanted an all-purpose telescope, a telescope that not only could carry on that work of measuring the positions of stars, but could do other projects such as photometry, measuring the exact brightness of objects, and spectroscopy, breaking the light of objects into its component colors to determine what they're made of and whether they're moving towards us and away from us and how quickly they're moving. So the Astronomy Department built this 31-inch general-purpose telescope in 1967. This is a reflecting telescope. At the bottom down here, it's got a 31-inch mirror, so the light comes in through the top of the telescope, bounces off the primary mirror, goes up, bounces off the secondary mirror, and then comes down to the camera that's located down here at the bottom. Now, in 1967, this telescope was used primarily with photographic plates, glass photographic plates. These are pieces of glass that have chemicals laid on them that are light sensitive. It's very much like plastic film that you put in a camera, but instead of the chemicals being on plastic, the chemicals were located on glass. This telescope was used with glass plates up until about 2 decades ago, when the telescope was converted over to modern digital cameras. Now today, we can use a variety of instruments on this telescope. Our graduate students at the University of Virginia have built an infrared camera, a camera that sees in the infrared portion of the spectrum, beyond what we can see with our visible eyes, beyond the visible light that we can see with our eyes. And that camera is called FanCam. And as I said, that was built by our graduate students. We can also put very sensitive high-speed cameras on here, and this telescope has been used from everything from measuring and monitoring the brightnesses of stars to monitoring stars as planets pass in front of them, called a planetary transit, as the planet blocks a little bit of the light of the star, to even studying satellites in orbit around the Earth. So this is one of our general purpose workhorse telescopes here at Fan Mountain Observatory, and today it's used for a variety of projects. What's interesting about this telescope is it is still moved the old-fashioned way. You have to come into the dome, you have to grab the telescope by the handlebar, and you have to pull it and move it around by hand. Although we have a computer readout that can tell you where the telescope is pointed in the sky, it does not have electric motors that will automatically move the telescope to point. You have to do that by hand. Once you're pointed at the object that you're interested in, then you can clamp it in place, and a small electric motor takes over to gradually turn the telescope to cancel the rotation of the Earth. Here I am with the mount for the 31-inch telescope, and you'll notice that the telescope is mounted on an axle, and that axle is the polar shaft. It points to the North Star Polaris in the sky. Technically, it actually points at the North Celestial Pole. The bright star Polaris is not exactly at the pole, but a little bit less than a degree away from the pole. The goal for this axle is that as the Earth turns around the North and the South poles, and the sky appears to turn in the opposite direction around the North and South celestial poles, which are exactly above the Earth's North and South poles, this telescope turns around exactly the same axis. This axle is exactly parallel to the rotation axis of the Earth. And as the Earth turns from west to east, the telescope turns around this axis from east to west, and it cancels the rotation of the Earth. And that means that once we park the telescope and point it at an object in the sky, and we turn the tracking motor on, that motor will allow the telescope to stay on that object for many hours at a time. So here we are in the control room at the 31-inch telescope. So this is where the astronomer would sit while they're doing their exposures. As I mentioned, to move the telescope, they'll have to go into the dome and point it by hand. You'll also notice that there are a lot of projects going on. People often have this picture of scientific observatories or scientific laboratories as being neat, with everything put away in its place. But here at Fan Mountain Observatory, we're often working on many projects at once. There could be 2 or 3 different cameras, one being worked on while one is being used, getting ready to swap the 2 of them out. And so you see here some cameras that are getting ready for use on the 31-inch telescope. Like the 31-inch telescope, the 40-inch telescope is mounted equatorially. That means that it too has a polar shaft that points to the North Pole in the sky. And as the Earth turns from west to east, the telescope turns from east to west. This is a fork mount. The telescope is mounted on a giant fork. There are 2 large fork arms, but the fork arms themselves are mounted on this axle. And this axle points right to the North Star up there, or the North Celestial Pole up there in the sky. Now the telescope is located inside of a dome. And the purpose of the dome is to protect the telescope from the wind and rain and ice and snow. It keeps the elements out of the dome. It keeps all the electronics and keeps the telescope dry. When it comes time to observe in the evening, we need to open up the dome. Here at the 40-inch telescope, we still do that manually. We climb a ladder, we turn a little lever, and we let a motor do the work to open it up. So let me demonstrate how we open and close the dome slit here on the 40-inch telescope. Once the dome is open, it's the astronomer's job then to keep the telescope pointing out the dome all night long. Here at Fan Mountain Observatory, the dome and the telescope are controlled from the control room, which is just below us, and we'll take you down there in a minute to take a look at it. This is the room where the operator sits when controlling the 40-inch telescope. So you can see here there's a bank of monitors and televisions that we use for monitoring where the telescope is pointing in the sky. There's a television and a computer that monitor the instrument that's attached to the telescope that's collecting the light from the telescope, and the astronomer can sit here and analyze that. And then there's a rack of electronics and computers over here that are actually controlling and moving the telescope. The telescope is one floor above us, and one advantage to modern astronomy is that you can sit in a warm room like this on a cold winter's night when the telescope is out in the cold working. The astronomer is comfortable sitting in here in the control room. I'm now standing 2 floors below the 40-inch telescope in the room that houses Phobos, the Fan Mountain Observatory bench optical spectrograph. The reason that Phobos is here and not mounted on the telescope is because it's much too big to mount on the telescope. Phobos is a spectrograph, and a spectrograph is a device that breaks light into its component colors. And astronomers do this for a couple of reasons. One of the reasons that we do it is that every element on the periodic table of elements absorbs and emits different colors of light. By breaking the light of stars into their component colors, we can tell what stars are made of. We can tell what elements are in them. And it's not just stars, but it's glowing clouds of gas and dust, galaxies, and many other objects. We can break their light apart and see what they're comprised of. The second reason for breaking light into its component colors is to see whether the object is moving towards us or away from us. Thanks to the Doppler shift. You're probably familiar with being in a car, and as an object, if a car is coming towards you, the horn sounds like it has a much higher pitch, and then as the car goes past you, it sounds like the horn has a much lower pitch. That change in pitch is called the Doppler effect. When objects are coming towards you, the waves are compressed to shorter wavelengths. When objects are moving away from you, the waves are stretched to longer, redder wavelengths. And the same thing happens in astronomy. If you know that a particular element absorbs or emits a specific color of light, and you see that that light is shifted towards the red, you know that the object is moving away from you. And if it's shifted towards the blue, you know that the object is moving towards you. And how much it is shifted tells us how fast the object is moving. And that's what's done here with Phobos. In the case of Phobos, we do both. We use Phobos for measuring what stars are made of, but we also use Phobos for determining the red shift or the Doppler shift because of the motion of the star. Now the way that Phobos works, the light from the telescope comes down on a little glass fiber called fiber optics. And it comes down and it goes through a lens that spreads the light out. The lens comes to the grating right here, and the grating is a piece of glass that has thousands of perfectly straight lines carved into it, scratched into it. And that grating spreads the light out into its component colors. And that spread out light goes through a separate set of lenses called the camera lenses that are then imaged onto the digital camera. And this is the digital camera that we use right here. It's not mounted in the proper place right now. It's shifted over because the camera is being worked on. But it is this grating that does all the work of spreading the light into its component colors, and then the camera picks that up, and then all of those signals are sent to the room above us where the operator can look at them. So Phobos has been used for a variety of projects. Probably the largest project it has been used for is measuring stars in our Milky Way galaxy, and seeing how those stars are orbiting around our galaxy in order to determine their history and how it is that they got to be orbiting the way they are in our Milky Way. This is the 24-inch robotic telescope here at Fan Mountain Observatory. The telescope itself is owned by Norfolk State University. They wanted a telescope, but they didn't have any dark sky location for it, and so they collaborated with the University of Virginia to build it here at Fan Mountain. They own the telescope, but we run and operate the telescope for Norfolk State. It's a 24-inch reflector, and I'll take you inside in just a second to see it. But it's important to know that this is a fully robotic telescope. We do not have to be here on site to run the telescope. All of our other telescopes that we've seen today, the 31-inch telescope, the 40-inch telescope, somebody has to be here when the telescope is running. But here at the Rapid Response Robotic Telescope, the telescope is controlled by computers that look at the weather, and if it's a beautiful clear night as it is now, the telescope automatically opens itself up and it begins observing. During the day, you can give it a list of objects to look at, and the telescope will spend all night long going through your list. So while I'm asleep in bed, getting a good night's sleep, the telescope is up all night taking observations for me and dozens of students, or really hundreds of students, and dozens of astronomers across the world that can dial in and use the telescope. So behind me is the 24-inch Rapid Response Robotic Telescope. It is a 24-inch reflector. Down at the bottom, there's a 24-inch mirror. The light comes through the telescope, bounces off that mirror, up to the secondary, and then down through to the digital camera that's mounted on the bottom. Now this telescope has just one instrument, and that instrument is a nice digital camera. And this telescope is used by hundreds of UVA students. It's used by researchers across the world. It's used by astronomers in the astronomy department to take images of the night sky through a system called Skynet that's run out of the University of North Carolina at Chapel Hill. They run dozens of robotic telescopes across the world, and we have borrowed their software and we use it to run our telescope. Now, the goal of the Rapid Response Robotic Telescope was to rapidly respond to things happening in the sky. Decades ago, astronomers discovered that every now and then a burst of gamma rays would randomly appear somewhere in the sky. They were called gamma ray bursts. And astronomers didn't know what they were, and they were curious as to whether these gamma ray bursts ever gave off other kinds of light, such as radio waves or optical light or infrared light. A number of observatories around the world were designed to rapidly respond to these gamma ray bursts. Now, gamma rays don't make it through our atmosphere, so they are sensed by satellites in space. And when a satellite would sense one of these gamma ray bursts, it would send a signal down to Earth, and that signal would get sent out to robotic telescopes around the world through systems like Skynet and tell them to stop whatever they are doing right now, go to these coordinates in the sky that the satellite determined, and look to see if this gamma ray burst is giving off any optical light. And sure enough, some gamma ray bursts do in fact give off optical light. This telescope was designed to rapidly respond to those events so that we can study these gamma ray bursts and learn more about them. But typically, only one gamma ray burst happens somewhere in the sky every day. The rest of the time, the telescope is occupied doing experiments and taking images for students and faculty and staff at the University of Virginia, at Norfolk State University, and for researchers around the world.